Hi, my name is Chris McNamara. I'm going to talk about, as Tim mentioned, PowerWare packet processing. This is a joint presentation by myself and Dave Hunt, but unfortunately Dave couldn't make it today, so credit to Dave as well. Excuse me. We're both working with Intel in the software group, so what we're about really, or why we're here today, is I think everybody will know in the room is that the demand for data is, increasing, and I keep hitting the clicker. There's a significant increase for data, which is giving us an opportunity. I'm not touching that, right? Is that me? Is someone else got a flicker out there? I'll leave it here and see if it moves, right? But ultimately, what we've been looking for our work here has been the opportunity to try and make DPDK green and more energy efficient, right? So look, I didn't touch it. Who's got it? I don't know, God. Okay, I got to talk faster. So ultimately, as we know, DPDK is polling 100% of the time. And the initiative that we're going to talk about is about how can we reduce that and bring it more in line with the network and the traffic that's happening in the network today. So how do we make it an on-demand DPDK, all right? And you obviously see the benefits of energy efficiency and increased performance. So we've been updating DPDK to support those use cases. And some of those, as you can see, have been updated into 17.11. Now, I'm on to the slide number 2. So if you look at this as an example, you can see that what we're trying to show here with an illustration is that the load on the network varies over time, okay? And as that load varies, it provides opportunity for energy efficiency, and it also provides opportunity for increasing performance when you need it, okay? So if you look at the green bars, you could have an example where your network's very quiet at nighttime, and during the daytime it's very busy. But what you really want to be looking at here is that 120% bar where the system is busy. Are you dimensioning your network for the worst case? And what controls or what toolbox do we have today with DPDK to allow us to increase the performance of our platforms to meet that expected or unexpected burst, okay? So really what we're trying to do here is meet that wave of data when it comes to us, all right? Okay? All right. So as we start moving towards a greener DPDK, how do we evaluate our system? And the screen has gone off. Okay, this is a comedy show, right? Okay, no, what are we on? Okay, so someone is in trouble, right? So if you look at what we're showing here, how do you evaluate your software, okay? You evaluate it under 3 criteria. Okay, the benefit, or the power that you can save, the energy efficiency, or the performance that you can apply. But also you have to consider latency and packet loss. And as you look at the graphic on the right-hand side of the screen, then you can see that increasing frequency is obviously, going to give you more capability, but it's also going to consume more energy or more power, okay? So what we have to consider is the latency and the loss associated with these types of capabilities, okay? But ultimately, again, we're trying to match the load on the network or the platform to the, to the compute capability in this scenario, okay? Now, once you start looking at what do we have today from a DPDK point of view, we've got the ability to manage frequency, okay? Typically from, I don't know, right? I'll just keep talking, right? So in DPDK today, we've got the ability to match the frequency to the up-down, right? So what we've added is the ability to allow platform capabilities like Turbo Boost, right? So what we can do is we can increase the frequency in shaking heads, no, it's like hand waving time. So timer? Yeah, any PowerPoint engineers? So if you look at the right-hand side and you think about those capabilities about going from the previous capability to the new capability and how to evaluate it in loss and, the energy and the packet, the latency. The previous layer 3 forward scheme that was there had a very good bar for the energy efficiency. But the queue depth that it was operating on, which was essentially the decision criteria, was a little bit shallow, which meant that we were seeing some false positives with respect to the ability to react and scale up quickly, okay? So when you start looking at the existing scheme, it's very important to measure the loss and the latency is what I'm saying, right? Now, you'll see here it's just a graphic over time. It shows that the layer 3 forward power scheme that was there originally did a good job of managing that from an energy consumption. And what we've also added is the ability to turn on turbo and increase the frequency of those cores. If you think back to that network diagram where we showed the 24-hour profile, when you want to enter, your system becomes oversubscribed and you want to enter a higher frequency mode, that you have that ability there today as well. Now, okay, so we talked a little bit about some of the things to watch and some of the potential benefits, but we also need to look at some of the challenges, okay? Now, some of the challenges to maintain always on, so things are easier, right? General rule of thumb, you can turn something down rather than turning it off. It sometimes becomes harder to bring it back to life and turn it on again. So we've been looking at this from turning down the power of the platform and using frequency scaling to reduce the power consumption of certainly the CPU, right? But ultimately, when you turn things down, we have to be able to scale up quickly. That's one of the challenges that I mentioned earlier around the buffering and the queuing that we have to be able to have a good time perspective on. Because if you look at that buffer depth in terms of time, and you look at 128 microseconds or 512 microseconds at 64 byte packet rates, it's going to give you 8 or 30 microseconds worth of time in that buffer. So ultimately, that's your reaction time. Because once that buffer fills up, you're going to suffer loss, right? So you need to be able to react very quickly. And that can manifest itself in a number of different ways. Now, once we kind of move on from some of those challenges and we start looking at what would an ideal scheme look like, of course, what we're recommending, what I would recommend anyway, would be that we have to be deliberate and control the change, okay? We have to make sure that when we change our power state, that we're doing it on purpose. And if you look at some of the Linux schemes that are there today, then they're not very favorable, that they take a long time to cycle through change and make that change. So we want to be very fine-grained and very reactive, okay? So we're saying, control the change and do it when you need to change, right? But we've given the APIs, and they're provided there in DPDK today. We've added those APIs to manage the power. But ultimately, it will depend on workload what the KPIs are for your workload. What are the decision criteria when you want to change that? And what I suppose the kind of interesting, or one of the kind of architectural changes that were made, okay, so we have the APIs for frequency management, we have the new APIs we've added for turbo, but what does the architecture look like to allow us to take advantage of a scheme, okay? Now, this picture here, what you're seeing is you're seeing two guests, and those guests are delivering a policy to what's shown as a VM power monitor here, which is a DPDK application. And what that's doing is it's managing the power on behalf of those virtual machines, okay? Now, that, in a sense, is a power governor that's running on the host, okay? The piece here that changed, I suppose, is that you can see here it's Virtual Serial, which is in past been used to pass commands from the virtual machine. So the virtual machine is saying, I want to change power. In this case, we're saying, here's the criteria, and you go manage them on my behalf to the VM power monitor, which is a nuance, but I suppose there's two real reasons for doing that. And the first one of those reasons is that the closer you are to the hardware, the faster you can react, okay? And by the time, for example, if you got a microburst or a burst of packets into your system, by the time you detected that, then, and it's gone up into the VM, and the VM has told you to go back and change it, it takes a lot longer than doing that at the host level. So that control system is a lot quicker, closer to hardware. And we saw in the range of, 2 millisecond time using these DPDK L3 forward power down to around 500 microseconds in terms of reaction, okay? So the second thing is there's a lot of waste. So if you've got 10 VMs in your platform, and each one of those is trying to monitor power control on your behalf, or if you're monitoring in each of those virtual machines, you have 10 instances of the same monitoring. So what we look at from this new architecture is what we're seeing here is in-band policy control for power, right? So the virtual machines can tell the host and say, hey, this is the packet rate. This is my packet rate for high, medium, and low frequency. And the host manages it, just as an example, on its behalf, right? Now, we've pushed up the traffic rate. So one of the capabilities that we pushed up was the ability to change that, as I mentioned, based on packets per second. And the second has been on time of day. So if you know your platform is going to be quiet at night time and busy during the day, you can just manage that at a very coarse grain, if you like. But you still do need to have the response or the reaction. The reaction time is key. So you still need to be able to have a monitor that's there that's going to scale up quickly. Okay. Now, this is, I suppose, a change in the architecture that we have, and what we're looking forward is in 18 releases. I won't commit to which version is more workload based. So we've kind of done the traffic rates and the time of day. But ultimately, what we're trying to do is match the compute to the network load and try and meet that flow and provide that architecture to the community to be able to do that as well. Okay. The last piece, it's all working well now. For the last slide, I'd just like to acknowledge Emmanuel, Rory, Constantine, and John, who were, and Dave, of course, who was instrumental in this work as well. So thanks. Any questions? Sure. Don't ask me to change slides.
Thanks. Okay.
Thank you.
So what is the reaction time of the power governance here? Because this defines a queue depth somewhere where we have to survive any change in the system, in the traffic.
Yeah, the software reaction time is in microseconds, single-digit microseconds. So it's literally the time it takes to request that state change. Okay. Now, where it becomes longer is when you have to have a logic there that's maybe tracking packets per second over time. You may want to have a window, for example, that you're saying every millisecond I'm going to make that change, or every 100 microseconds I make that change. So it's cumulative. Does that answer a bit? Okay. Okay. Okay, good. Thanks very much for your time, and